In a mixture of gases, each gas has a partial pressure which is the hypothetical pressure of that gas if it alone occupied the volume of the mixture at the same temperature. The total pressure of an ideal gas mixture is the sum of the partial pressures of each individual gas in the mixture. It relies on the following isotherm relation: Vx is the partial volume of any individual gas component, VTOT is the total volume in gas mixture, Px is the partial pressure of gas X, PTOT is the total pressure of gas mixture, Nx is the amount of substance of a gas, NTOT is the total amount of substance in gas mixture. The partial pressure of a gas is a measure of thermodynamic activity of the gas's molecules. Gases dissolve, diffuse, and react according to their partial pressures, and not according to their concentrations in gas mixtures or liquids. This general property of gases is also true of chemical reactions of gases in biology. For example, the necessary amount of oxygen for human respiration, and the amount that is toxic, is set by the partial pressure of oxygen alone. This is true across a very wide range of different concentrations of oxygen present in various inhaled breathing gases, or dissolved in blood. Dalton's law of partial pressures. The total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases in the mixture as stated by Dalton's law. This is because ideal gas molecules are so far apart that they don't interact with each other. Most actual real-world gases come very close to this ideal. For example, given an ideal gas mixture of nitrogen, hydrogen and ammonia. Ideal gas mixtures, ideally the ratio of partial pressures equals the ratio of the number of molecules. That is, the mole fraction of an individual gas component in an ideal gas mixture can be expressed in terms of the component's partial pressure or the moles of the component. And the partial pressure of an individual gas component in an ideal gas can be obtained using this expression. The mole fraction of a gas component in a gas mixture is equal to the volumetric fraction of that component in a gas mixture. Partial volume. The partial volume of a particular gas in a mixture is the volume of one component of the gas mixture. It is useful in gas mixtures, for example air, to focus on one particular gas component, for example oxygen. It can be approximated both from partial pressure and molar fraction. Vx is the partial volume of any individual gas component, VTOT is the total volume in gas mixture, Px is the partial pressure of gas X, PTOT is the total pressure of gas mixture, Nx is the amount of substance of a gas, NTOT is the total amount of substance in gas mixture. Vapor pressure. Vapor pressure is the pressure of a vapor in equilibrium with its non-vapor phases. Most often the term is used to describe a liquid's tendency to evaporate. It is a measure of the tendency of molecules and atoms to escape from a liquid or a solid. A liquid's atmospheric pressure boiling point corresponds to the temperature at which its vapor pressure is equal to the surrounding atmospheric pressure, and it is often called the normal boiling point. The higher the vapor pressure of a liquid at a given temperature, the lower the normal boiling point of the liquid. The vapor pressure chart displayed has graphs of the vapor pressures versus temperatures for a variety of liquids. As can be seen in the chart, the liquids with the highest vapor pressures have the lowest normal boiling points. For example, at any given temperature, methyl chloride has the highest vapor pressure of any of the liquids in the chart. It also has the lowest normal boiling point, which is where the vapor pressure curve of methyl chloride intersects the horizontal pressure line of 1 atmosphere of absolute vapor pressure. Equilibrium constants of reactions involving gas mixtures. It is possible to work out the equilibrium constant for a chemical reaction involving a mixture of gases given the partial pressure of each gas and the overall reaction formula. For a reversible reaction involving gas reactants and gas products, such as the equilibrium constant of the reaction would be. For reversible reactions, changes in the total pressure, temperature or reactant concentrations will shift the equilibrium so as to favor either the right or left side of the reaction in accordance with Le Chatelier's principle. However, the reaction kinetics may either oppose or enhance the equilibrium shift. In some cases, the reaction kinetics may be the overriding factor to consider. Henry's law and the solubility of gases. Gases will dissolve in liquids to an extent that is determined by the equilibrium between the undissolved gas and the gas that has dissolved in the liquid. The equilibrium constant for that equilibrium is 1 AA. The form of the equilibrium constant shows that the concentration of a solute gas in a solution is directly proportional to the partial pressure of that gas above the solution. This statement is known as Henry's law, and the equilibrium constant is quite often referred to as the Henry's law constant. Henry's law is sometimes written as 2 AA, whereas also referred to as the Henry's law constant. As can be seen by comparing equations and above, is the reciprocal of. Since both may be referred to as the Henry's law constant, readers of the technical literature must be quite careful to note which version of the Henry's law equation is being used. Henry's law is an approximation that only applies for dilute, ideal solutions and for solutions where the liquid solvent does not react chemically with the gas being dissolved. Partial pressure in diving breathing gases. In recreational diving and professional diving, the richness of individual component gases of breathing gases is expressed by partial pressure. Using diving terms, partial pressure is calculated as, partial pressure equals A, for the component gas I, PPI equals P A, phi. For example, at 50 meters, the total absolute pressure is 6 bar and the partial pressures of the main components of air, oxygen 21% by volume and nitrogen 79% by volume are, ppn2 equals 6 bar, 0.79 equals 4.7 bar absolute, ppO2 equals 6 bar, 0.21 equals 1.3 bar absolute, the minimum safe lower limit for the partial pressures of oxygen in a gas mixture is 0.16 bars absolute. Hypoxia and sudden unconsciousness becomes a problem with an oxygen partial pressure of less than 0.16 bar absolute. Oxygen toxicity, involving convulsions, becomes a problem when oxygen partial pressure is too high. The NOAA diving manual recommends a maximum single exposure of 45 minutes at 1.6 bar absolute, of 120 minutes at 1.5 bar absolute, of 150 minutes at 1.4 bar absolute, of 180 minutes at 1.3 bar absolute and of 210 minutes at 1.2 bar absolute. Oxygen toxicity becomes a risk when these oxygen partial pressures and exposures are exceeded. The partial pressure of oxygen determines the maximum operating depth of a gas mixture. Nitrogen narcosis is a problem when breathing gases at high pressure. Typically, the maximum total partial pressure of narcotic gases used when planning for technical diving is 4.5 bar absolute, based on an equivalent narcotic depth of 35 meters. In medicine, the partial pressures of particularly oxygen and carbon dioxide are important parameters in tests of arterial blood gases, but can also be measured in, for example, cerebrospinal fluid. See also: breathing gas, Henry's law, ideal gas and ideal gas law, mole fraction and mole vapor. References